Okay, so we've got our standard tank system. And we're assuming that all of these flow rates are just volumetric flow rates to keep things really simple. We don't want to worry about densities and so on. The mass balance simplifies to a volume balance. And we have the geometry of the tank that relates the level to the volume. Okay, so at this point, we have a nice linear differential equation. Now, let's assume that what we're trying to do is to predict the level, or what will happen to the level when the flow rate in undergoes a step change, in other words, a very brief or immediate change in flow rate in an upwards direction. Okay. So what we're going to do is first we're going to find a differential equation that, a single differential equation that relates the level to the input that we're wanting to do. And what we're wanting to do, in other words, is to eliminate the volume from the equations. So we're going to substitute the volume into there, and that will make the volume go away as a variable in our model. And we're going to get rid of f out as a variable by substituting it in there. And after all of those substitutions, I end up with a dH dt is equal to f in minus kh. Right, so now we have a single differential equation which will have this property that if I change f in, I will be able to solve that differential equation to obtain the response of the system level. Right, and so when we started the subject, there's already a Jupyter notebook on the repository which solves this using SymPy directly. In other words, it takes the differential equation solution ability of SymPy, stays in the time domain, doesn't do any kind of transforms or anything like that, and just applies that directly. Now, what we're going to do is we're going to first rewrite this equation in terms of deviation variables, and then we're going to do the Laplace transform. So rewriting this linear differential equation, and because it's a linear differential equation, this will always happen. We will always end up with a equation which is exactly the same, but only has the deviation variable substituted once we do the deviation variable substitution. So remember, the deviation variables are defined as the original variables minus their steady state values. And that leads to this kind of substitution that we can make, which says that the original values are equal to the deviation variables plus their steady state values, right? And now we're going to substitute that into both of the h's in that equation, and that will lead to, we're also going to substitute in the deviation form of f in, which is defined exactly the same way, right? So we're going to have here, so I've done my deviation variable substitution, and I'm now going to simplify. You'll see this pattern emerging basically every single time that we do a problem like this, right? The first thing is that the derivative of a deviation variable is the same as the derivative of the original variable. This is just because we're adding a constant, right? And so that will always simplify in this way. Now I'm going to just keep the deviation variables kind of on one side of this equation so that I've got all the steady state variables in a place where I can easily cancel them out later. So I'm just going to have f in prime over here minus kh prime. And I want you to realize that part that I've written down now is now exactly the same as the original equation in form. The difference is that there's this extra bit, right? So there's f in bar minus k h bar. There's that term. That's the difference between these terms, right? But move this up a little bit and say, right, at steady state, right, if I rewrite that same equation over here, let's call that equation 1 becomes a dh dt, which is equal to 0, right, is equal to f in bar minus kh bar. Why am I writing the bars? That's the definition of the bars. So those are the definitions of steady state, right? At steady state, the derivatives are 0. That is what steady state means, right? Nothing is changing. At steady state, nothing changes. That's the definition of steady state. And we have these nomenclature definitions that I add in as well. Okay, so at steady state, we now know that upon a little bit of simplification, that means that f in bar minus kh bar is equal to 0. That this whole group here is the same as this whole group there. And so the net effect of introducing deviation variables on a linear set of differential equations is that I obtain an exact copy of the same equations written out with primes in the places of all the time-varying variables. Okay? Does everybody see the similarity, right? Look at the symmetry between these two equations. I've got this equation over here, which is the version that I started out with, and I've got this equation over here, which is what's left after I've substituted deviation variables. It's the same equation, same form of equation, except that we are now in deviation variables. Okay, so that is like step 1. Step 1 is I've introduced my deviation variables, and I've done this for a very specific reason, because I want to attack this problem. Remember, the big problem is I have this tank. It's described by these differential equations. F in undergoes a step change. In other words, it goes from whatever its steady state value was rapidly up to a new value. And my goal is to figure out what h will do when that happens. In other words, I'm trying to solve the differential equations for a function of time, h of t. And I will approach this now differently from the way that we did it when we used SymPy. We won't use integrating factors or known solutions of first-order differential equations or anything like that. We will proceed by using the Laplace transform. So the reason why we've introduced deviation variables in the first place is because we would like to use an identity from the Laplace transform that says the Laplace transform of some derivative with respect to time is equal to the Laplace transform of the function of time times s. So this is a very useful property of the Laplace transform, and effectively it's the thing that most people remember about the transform, right? If you recall, the reason why you used the Laplace transform in differential equations is because the Laplace transform had this wonderful property that it took differential equations and it transformed them into algebraic equations. And this identity is the reason why. Now, there's an extra bit, whole sum term, and the only thing that you need to remember is that there's an x0 in there. And this will be equal to 0 for deviation variables. And in fact, this property is effectively the only reason why you ever want to use deviation variables when you're working with the Laplace transform. But it is an incredibly useful property because it allows us to ignore all of these additional constants. So for a relatively straightforward procedure, we get quite a large gain, which is that this term effectively always disappears. And the version of this identity that you really need to remember is the Laplace transform of the derivative of a function is just equal to the Laplace transform of the function times s. And I recommend, even though you have the table, the insight that you obtain from having this fact readily available in memory makes it worthwhile to memorize. And now we'll talk about properties of the Laplace transform a little bit later, but this is, if you remember one identity for the Laplace transform, this should be it, right? That the Laplace transform of a function, of a derivative of a function, is the Laplace transform of the function times s. Now, this has a wonderful effect, because if I now call this equation 2, if I Laplace the whole of equation 2, right, I first Laplace the left-hand side, and I'm just keeping the a there just to make the writing out easier. The Laplace transform is an integral transform. That means it's a linear transform, and that basically means that constants will migrate out of the transform. And so I can write equation 2. I'll write it out longhand just the first time. So I'll have the Laplace of a dh prime dt is equal to the Laplace transform of f in prime minus k h prime. And now we'll use some properties of the Laplace transform. It's easier to remember for me personally how the Laplace transform behaves by remembering that the definition of the Laplace transform is in terms of an integral. So the Laplace transform is defined as the integral from 0 to infinity of f of t times e to the minus st dt. Right? So that's easier. If you think about it, this is an integral. This explains most of the properties that we're going to use now. It explains why the constant over here will migrate out of that integral. So this constant will, I can just write that over there, right? It also explains why this distributes over this sum, right? So it explains, because I'm doing an integral, it's the same property that says, well, if I'm doing an integral of a sum, I can just do the separate integrals separately, right? So everything that you know about integrals, you already know about the Laplace transform, because the Laplace transform is an integral transform. So you don't have to remember them separately, right? And so because of this, let's say this is just like parenthetical, just like a little bit of a reminder of why this is happening, I can simplify this as a times the Laplace of dh prime dt is equal to the Laplace transform of f in prime minus k times the Laplace of h prime. And because of the previous property that I just wrote down earlier, that means I have a times h of s times s is equal to f in of s minus k times h of s. So you should be wanting to move to a position where this comes incredibly quickly. I expect you to be able to do this kind of stuff with the Laplace transform without even thinking about it. It's super simple, it's all linear. So once we have a set of linear equations, now this is effectively this notation over here, this big H. That is just how we write the Laplace transform of an unknown function. Right? So we'll just have a Laplace transform of an unknown function. Are you saying why does the big H not have a prime? I could put a prime, but what is going to happen very frequently is we're going to go through these steps so often, and almost all of the problems that we'll solve will be in terms of deviation variables, that we will we will eventually reach a point where I will just say, I've rewritten in terms of deviation variables and I won't write the prime. And it will kind of be, the prime will be implied. It is an important point when we actually get numeric results, but you'll see very seldom that we actually do the primes. Once we get past this part where these things are a little bit still fresh and new, we'll stop writing primes, and we'll just start writing the variables as though the variables without the prime were the deviation variable. It's only confusing for like a little bit. Okay, so now we have this, and I'm going to go one step further in order to obtain what is called the transfer function form. And I'll explain why this is useful once we actually then solve this problem. Okay, so the transfer function form is a way of separating out the effect of the variables and the effect of the system. And what we're going to do is we're going to just manipulate this equation so that I take out, so that I get the variables just isolated by themselves. And what we typically want to do is we want to have a function which has the property that I can multiply by the input in order to obtain the output. And this is what it's called a transfer function. So to do that, I'm going to manipulate this. I'm going to take that to that side and that to that side. Now, this construct, this ratio between the output and the input, is called the transfer function relating h to Fn. So this is commonly called g of s. And what you'll find is that we will be able to write h of s is equal to g of s times Fn of s. And we commonly represent this in a block diagram like this. And so you'll find yourself talking about that transfer function as representing the system. You'll see that everything in the transfer function came from the differential equations representing the system, while everything in these signals, so this and that, we often will call signals, just because it comes from a little bit of electronics, but let's call them the variables. These variables Fn and S, or Fn and h of s, they have been separated out of this problem. I only have to do this analysis once for this particular system, and what this allows me to do is to avoid reanalyzing the system with different versions of the inputs. Sorry. We basically talk about the box as the system, right? And in other words, you can tell yourself, I've got a system which is describing, I've got a system which is the physical thing. And I've got the inputs and outputs, which are the measurements or let's say the information about what is changing to make that system change from steady state, and the measurements that I have of how those things are changing when they change. And so in almost all cases, when we actually analyze a system like that, we'll be talking about measured versions of these signals. And so that's why we often use the word signal, because they're often signals from electronic equipment. Whereas the system itself, the physical stuff, the tank and the water and all of that stuff, that is out there in the real world, and it is described by these differential equations. And what we've succeeded in doing is to capture the dynamic behavior of the system in this one expression. And you'll notice that there's nothing in that expression about h or f. In other words, it's not specific to a particular change in f, and it's not specific to a particular change in h. What this allows me to do is do this analysis exactly once. I can then answer all the kinds of questions that I want to ask about the simulation problem without doing any additional reanalysis up to this point. I've got the transfer function, and solving for h of t becomes simple now, because I take my f of t, I take f in of t, which I'm going to say is something like this. Now that's known as the unit step. This function has a known Laplace transform in the table. So I don't have to do anything very special to get that Laplace transform. I simply say, here is what that function is in the table. Its corresponding Laplace transform is 1 over s by virtue of the table. We don't have to prove it, right? And what does that mean? I now have a Laplace domain expression for h of s, right? Because I've got this, that's g of s, and I've got, so remember I said h of s is g of s times fn, right? I've already figured out what g of s is, and I now substitute fn of s, which is 1 over s, right? We've taken the original differential equations, we've introduced deviation variables, we linearized if we needed to. We've Laplace transformed the differential equations and found the transfer function. We've Laplace transformed the input. We now calculate the output by multiplying those two together. We now have h of s. To find h of t, we now do the inverse Laplace transform of h of s. Now, we can do that in two different ways. We can notice that there is exactly this kind of thing in the table. So over here in the table, you'll see exactly the kind of thing that we have here, right? So we've got kind of a 1 over s. We've got a 1 over s times something with a coefficient of s plus another thing, right? And that's the form that we'll use here. And so we'll see that it will form this shape, 1 minus e to the at multiplied by a constant. So effectively, we know that that will be some constant times 1 minus e to the minus some other constant t in form from the table. Right, so that just is coming from the table. We can also do exactly the same inverse transform using SymPy, which I'll show you tomorrow. But I want everybody to follow the steps, right? I'm just going to recap very quickly again. We started with a problem stated in terms of a picture. We wrote down the differential equations in natural variables. We linearized if necessary and introduced deviation variables. After introducing deviation variables, we calculated the Laplace transform. Once we had the Laplace transform, we isolated the variables so that they occur only once in the expression. We separated out the variables and the remaining expression to obtain a transfer function. Right? The transfer function is defined as the coefficient of the input in an expression written in this way with the output on the left-hand side. This enabled us to then take the Laplace transform of the input signal, multiply out, and take the inverse Laplace transform to solve the equation. We're going to use this exact procedure to solve all the differential equation solving that we'll be doing in this subject. So if you kind of follow this, I will be uploading this video as well, so you can have another run at it. But this is the full process, going from problem statement all the way to solution.